okay. So, let us come with the same thing, that load frequency control continuation. Next one is a governor, so speed droop characteristics, right. So, up to this we have seen that it is a valve in case of your steam turbine, or hydrograte in case of hydro plant, right. That is why I have written steam or water, what actually for a hydro power plant, right. This turbine shaft to generator, and this portion is on your one gain is there, then integrator, and one additional feedback loop R is used there, right. So, governor with steady state feedback with one feedback is there, that is we call, later we will see this R actually we call it your speed regulation parameter. So, this feedback is taken, right. Once you do this, and this one already I told you that this is the shaft. So, your speed or frequency is being sensed from the shaft, because the generator and turbine is coupled together and is rotating, right. If it is a 50 hertz system, then it is rotating at 3000 synchronous speed, synchronous generator rotate at synchronous speed at 3000 rpm, right. If it is a 50 hertz system, right, and therefore, we are sensing the speed or the frequency. If you sense the speed, that is omega is equal to 2 pi f, hence frequency also, right. So, and this is the reference set point, this is the reference frequency, and difference is delta f. What I will do is delta f capital I have written, but we can take delta f small, because this is small, this is small. So, it does not matter whether it is capital or small, both are same, right. And this additional feedback, that speed governing parameter R, we call speed regulation parameter, this feedback is taken. Now, what we will do? So, when two or more generating units are connected to the same system, right, then isochronous I told you, it means a constant speed cannot be used, since each generating unit that would have to be precisely the same speed setting, right. That means, if you go for, suppose you have two or more generators, the reference speed setting has to be same, but when you are setting it manually, it may not be accurate. So, there will be tug of war. If two generators are there, then between the two generators, and if you have more than two generators, then among the generators that there will be tug of war, everybody will try to set the frequency in its own setting. So, to avoid that, this speed regulation parameter is used for each generating unit, right. Otherwise, that is why I have written, otherwise they fight with each other, each will try to control system frequencies to its own setting. I mean, this is the setting. So, if you have more than two or more generators, then everybody will try to set its own setting, right. So, that is why this speed droop characteristic is used. So, for stable load division between two or more generating units operating in parallel, the governors are provided with characteristics so that the speed drops as the load is increased. That means, this feedback is required, right. And the regulation or speed droop characteristic can be obtained by adding a steady state feedback loop around the integrator as shown in figure 4. This is figure 4, and around this integrator, the steady state your what you call feedback is used, right. So, when you use this is actually we call speed regulation parameter, or later we will see. So, now the transfer function of the governor figure 4, that means only this portion we will see now, only this portion, turbine generator we will see later, this side we will see later, but only this portion, this is the output of the governor valve delta capital E, this is the output, right. So, reduces as shown in figure 5, that means here what I am doing is, this is this portion, as when you look into this thing, this portion to your right hand side and this is to left hand side, but what we will do, this portion will this one will make it 180 degree shift in making the block diagram. So, this portion will come to this side, this portion will come to this side, but meaning is same, everything is same, just look. So, this is your delta f, this is f r minus r. If you look into this delta f is that your what you call, this is same thing, that small delta f, same thing, right, capital delta f. So, this is your, this side you are making f minus f r, the output is delta f. So, look, this is delta f, that means this right hand portion we are making from the left side, right, that is all. So, and then this is the gain and this is the integrator. So, this is the gain, and integrator means 1 upon s, and look output here, it is delta E, that is output of the valve position delta E. So, this is delta E, and the steady state feedback, this R coming here, left hand side it is like this, but as we have taken to this side this side that is why it is your what you call this way, it is minus R. So, minus delta F. So, this is actually minus delta F, and there it is minus your R feedback. So, it is minus delta f and minus R, right. So, this is your what you call the block diagram of the governor. Governor means all this portion, right, this portion. If I make it like this, I mean this portion is the governor part, this portion, right. So, once you make this one, and this right hand side, actually we have made it to the what you call the left hand side, because we will move from your what you call that your governor, then your there is steam valve or governor, then we will move to the turbine, then we will move to the generator part, right. So, that is why this, but this block is same, this one and this one is same, only this portion has been brought to this side, I mean from this way. So, if you your what you call try to take the your reduced block diagram. So, here I have written that it is delta f, then it is minus 1 upon R. If you reduce it, and it will be 1 upon 1 plus S T G, and this is delta E. How things are coming? Just look into this. That suppose this is the block diagram, and this is minus delta f, this is minus R. So, it will be basically minus delta f plus R into K by S, right. So, here it is delta E also it is here. So, it will be look minus your delta f, right, this one, and then your what you call this is delta E, input is here. So, R delta E. So, minus R delta E. So, minus R delta E bracket close into K upon S, right, integrator, and this is the gain, into K upon S, right, is equal to that output delta E. So, delta E is equal to your this one minus delta F minus R into delta E into K upon S is equal to delta E. If you simplify this, then it will be S into delta E is equal to minus K into delta F minus K R into delta E, or S delta E plus K R delta E is equal to your minus K into delta F, right. Therefore, you take delta E common. So, it will be K R I am writing first plus S delta E is equal to minus K into delta F. Now, what you do, both side you divide by K R. So, it will be, if you divide by K R both side, it will be 1 plus 1 upon K R into S, right, into delta E is equal to minus K upon K R into your delta F, or your what you this K will be cancelled. Therefore, and define that T G is equal to your what you call 1 upon K R. You define T G, right. So, your what that means your this one you can write 1 plus S T G is equal to minus delta F upon R, right. The delta E I have missed here, delta E. Therefore, delta E is equal to minus delta F upon R into 1 plus S T G, right. That is why this block diagram is written delta F minus 1 upon R into 1 plus S T G, right. So, in this case just have a look, just 1 minute. So, what if from this one, right, this is written like this, that means this one we can write like this, no, delta E is equal to, we can write like this, minus 1 upon R into 1 upon 1 plus S T G into your delta F, this way you can write. Therefore, this block diagram also made it like this, delta E is equal to minus delta F upon R into 1 upon 1 plus S T G. That means, this equation if you put in the block diagram form, then this will be your input delta F, and this will be your minus 1 upon R into your 1 upon 1 plus S T G. So, into your 1 upon 1 plus S T G, right, output is your delta your F, right, sorry, delta E. So, this is your delta F, that is that your this input the delta F into. So, same block diagram, same thing that I showed you, all this simple derivation I showed you here, right, how we are getting it. That means, your this delta E is equal to minus your delta F by delta F upon R into 1 plus S T G. Then what is T G? And T G I told you, T G is equal to 1 upon K R. This is actually sometimes we call governor time constant, right. It is in second, right. So, that means this is reduced block diagram. So, this is actually governor transfer function of the governor part. This delta F is coming from where, that we will see later when everything will be completed. So, this is actually block diagram of speed governing governor with droop characteristic. This R we call speed droop characteristic, or sometimes we call regulation system regulation parameter, right. That is why R is speed regulation parameter, or sometimes we call droop, and T G is equal to 1 upon K R, that is governor time constant, right, T G. Next is this is the speed regulation, that is R. So, the values of speed regulation parameter R, it determines the steady state frequency versus load characteristic of the generating unit as shown in figure 6. So, actually this whatever value we will choose, right, that actually determines the steady state frequency versus load characteristic of the generating unit as shown in figure 6. How? Slowly and slowly we will see this. So, if you look at figure 6, right. So, delta F, I here no this F minus F 0, what we take, I think it should be F 0 minus F, right. So, not this one. So, whatever you take, suppose you have a speed, this is the frequency, and F 0 is the nominal system frequency, say, right, and this is the power output in per unit, this is the maximum, say 100%. So, this is 1 per unit, and this is the speed droop characteristic. F 0 is the nominal system frequency. I mean, if the operating frequency is 50 hertz, then F 0 is 50 hertz. If the operating frequency is 60 hertz, then it will be 60 hertz, right. So, this is your that is that at no load, suppose this is your FNL, this is that operating frequency at no load, so slightly higher than your nominal system frequency, and this is that full load. That full load means, so when generating unit is loaded 100%, suppose it is 1 per unit, suppose your generating unit is 100 megawatt, and if it is operating at 100 megawatt, we are calling it the full load, and this is your FL, that is suffix is full load, FL means full load, and this FNL, this suffix NL means no load, and this is the nominal frequency. Now, characteristic is linear, right, linear characteristic, and this is your delta P, suppose change in power, suppose it is operating at some frequency F, say some this blue ink some frequency F. So, make an horizontal line. So, del F will be actually F 0 minus F, this F 0 minus F. So, R the slope, this because this is the slope. So, R will be actually this is delta F, this width is delta F. So, it will be delta F upon this power change is delta P, right. Suppose the idea is something like this. Suppose a machine was operating at a power at a nominal frequency F 0, right. At that time your what you call that power was, say it was P 1, and when that further load is increased, so at that time frequency will fall. If real power increases, frequency will fall. So, that is why suppose it has come down to F, and at that time this difference is P 2. Sorry, this power generation is P 2. Therefore, delta P will be here, if you write delta P will be actually P 2 minus P 1, right, and similarly delta F is equal to F 0 minus F. Therefore, slope of this characteristic R is equal to delta F upon delta P, it is written here delta F upon delta P, right. So, therefore, from that you can get that what is your what you call that the slope, this is a linear characteristic. So, and this is your 1 per unit means that your what you call that is your maximum your power generated by the generating unit, and this frequency is in hertz, although this is in per unit, and this is that this is the power output, and or we are writing valve or gate position. Listen, in per unit whatever, assuming it is a lossless system. So, in per unit whether it is a power output or voltage or gate position, it will in per unit they will remain same. Valve means steam valve or gate means that hydro gate. In per unit this will remain same. That is why I have written power output or valve / gate position, right. So, per unit your everything will remain same. So, second thing is, so this is a steady state characteristic governor with a speed droop, right. The speed droop means speed droop characteristic R. Now, therefore, here we are writing the ratio of frequency deviation delta F to change in valve or gate position, that is delta E, or power output delta Pg is equal to R. That means percent R, that is speed regulation by R, is equal to percent frequency change divided by percent power output change into 100. This is the equation 1. When we will take, for example, when we will take the numericals, at that time you will see, right. For example, a 4% droops or regulation means that a 4% frequency deviation causes 100% change in valve position or power output, right. Suppose your just for the sake of understanding, suppose your power generating maximum capacity is 100 megawatt and 4% droop or regulation means, suppose your system is your 50 hertz, that means it will be your 50 hertz into 4%. So, it will be your what you call, that is 2 hertz, right. So, in that case, that 4% frequency deviation means it will, that is 2 hertz, frequency will deviate 2 hertz from 50, that means it will become 48 if the generating unit is 100 megawatt, if you generate 100 megawatt, meaning is like this, right. If it is in power, but or in if it is in power unit, you can say valve position or power output, right. So, percentage R is equal to percent frequency change by percent power output change into 100, right. So, this is we have given equation 1, much more we will see later, right. Now, suppose you have 2 generating units operating in parallel. First you understand, then we will write up other things are given. Suppose 2 generating units are operating in parallel, this is the load sharing by parallel generating units, both having different speed droop characteristics. This generator has this kind of characteristic, this generator has this kind of characteristic, but it is a linear, right. So, initially, suppose initially the generator, it was operating at a nominal frequency f0, right, frequency. So, you draw horizontal line this thing, therefore, when it is operating your at nominal frequency f0, at that time it was generating power Pg1, this unit 1 generating power Pg1, at the same time this unit 2 was generating power Pg2. So, this is Pg1 for unit 1 and this is Pg2 for unit 2 when it was operating at nominal system frequency, say f0. F0 may be 50 hertz for 50 hertz system or 60 hertz for 60 hertz system, right. Now, suppose the load has increased, suppose load has increased. So, both the generators have to share the load. For example, suppose demand was 200 megawatt, right. Suppose suddenly load has increased from 200 to 210. So, 10 megawatt has increased and those 10 megawatt will be shared according to the droop characteristic of these 2 generators. So, similarly, suppose load demand has increased, so frequency will fall. Suppose this is Fc, it is given, right, change frequency Fc. So, for that case you draw a horizontal line, at that time according to the droop characteristic this generator is generating power Pg1 dash and similarly generator 2 is generating power Pg2 dash. That means your, and because of this change in frequency delta F will be F0 minus Fc, right. So, F0 minus Fc, but in this case in this case delta Pg1 will be Pg1 dash minus Pg1 and delta Pg2 will be Pg2 dash minus Pg2, right. Although delta F remains same, but this delta Pg2 and delta Pg1 they are same unless and until their droop characteristic they are different, unless and until their speed droop characteristic is identical, right. That means the delta Pg2 will be different than delta Pg1 or vice versa, right. So, in that case your what you call this if you try to take the speed droop, in this case R will be delta F upon delta Pg2, that is R2, and R1 in this case will be your delta F upon delta Pg1, right. So, delta F will remain same, but this generation your generator power sharing will be different. So, that is the load sharing by parallel generating units. I hope this you have understood, but one thing is there, this side when you are making it, generally we make it that your per unit. So, that is why this graph power output generating unit 1 and this is power output generating unit 2 and this side is frequency is hertz, it is given in hertz, right. So, load sharing by 2 parallel generating units with drooping governor characteristic, 2 different droop characteristic of the governor, right. Now, all these things, this is actually figure 7, this is figure 7. So, now all these things I have written, further I will tell you what exactly it is. If 2 or whatever I said I have written for you here, if 2 or generating units with drooping governor characteristic are connected to a power system, there must be a unique frequency at which they will share a load change. So, this is unique frequency with the 2 droop characteristic, it is although they are operating in parallel, right, and but their frequency is common, that is Fc, it is they operate at a common frequency, right. So, in this case, and this is the figure 7, the droop characteristic what I told you, this is the figure 7, this is figure 7, right. Initially they were operating at nominal frequency f0, this is at nominal frequency f0. Now, when they are operating, load has increased, so the operating another frequency, you can say fc is a common frequency rather than frequency change, it is a common frequency. So, they are operating at common frequency. So, there will be no tug of war between the generating units, but only generation, the power generation will be different for sudden increase of certain increase of the load, right. So, an increase in load delta PL causes the generating unit to slow down, and the governor increase your what you call that your in the case of your this thing, the output until they reach a new common operating frequency, that is fc. Actually in a power system, that when load demand is increases, I told you if load demand increases, the generators that whatever power demand increases, if you have 2 or more generators, that according to the droop characteristic, that generators will share the power whatever droop characteristic you have set for the your what you call for the generating units, right. So, the amount of load picked up by each unit depends on the droop characteristic. For example, just from this figure only I told you that delta Pg1 is equal to Pg1 minus Pg1 dash. Therefore, delta Pg1 is equal to Pg1 minus Pg1 dash minus Pg1 is equal to delta F upon R1, right. So, this is your delta F, the slope characteristic, that is your R1 is equal to basically delta F upon your delta Pg1. Other way we are writing delta Pg1 is equal to delta F upon R1. Similarly, for this one also R is equal to delta F upon delta Pg2, or other way you can write delta Pg2 is equal to delta F upon R2. This is equation 2 and this is equation 3. So, delta Pg2 is equal to your del Pg2 dash minus Pg2, right. So, is equal to delta F upon R2. So, this is equation 3. Now, if you divide equation 2 by equation 3, then you will get delta Pg1 upon delta Pg2 is equal to R2 upon R1. That means, look, the generation share that this generation sharing, actually it is inversely proportional, because delta Pg in general change in that delta Pg is inversely proportional to the speed regulation parameter. If delta Pg1 R1 is equal to actually delta Pg2 R2. So, this is equation 4, right. So, therefore, if the percentage of regulation of the units are nearly equal, the change in the output of each generating unit will be nearly in the proportion to its rating. That means, if R1 is equal to R2, then delta Pg1 will be equal to delta Pg2, otherwise not, right. Now, this is one thing. Next one is that your control, I hope this droop characteristic, why do they use the droop characteristic for each governor? I think it is now understandable to instead of isochronous governor, right, and those mechanism. So, control of power output of generating units. Now, you have the generating will generate power, but you have to control the your what you call output generating power. So, so the relationship between frequency and load can be adjusted, right, by changing the your input as shown as a load reference set point. This is called U in the figure 8. So, we will come back to that. So, this is actually it is a speed changer motor, right. Details will not go, just schematically we will show that it will act as an integrator, right. This output of U, actually it is output of an integrator. I have a different type of controller, not only integrator, different type of controller. So, this is load reference. So, same block diagram, everything is same up to this as it was, up to this as it was. If it is not there, it was like that, whole block diagram even same, but you have to what you call, you have to control the output of the generating power, your generating power output. Therefore, you need a load reference set point, this is we call U, right. So, this is the schematic diagram of governor and turbine with that load reference set point, and governor with load reference control for adjusting frequency and your load relationship, and this is your what you call if you only this portion, if you not turbine or generator, only this portion if you simplify, it will become actually delta F, that is 1 upon R U, your this U will become plus, then 1 upon 1 plus STG delta E. Now, how this your what you call these things are coming from this one? If you have seen this diagram, if you have just hold on, from that I will make it for you, just hold on, right. From this diagram, just hold on. from this is your schematic diagram without reference set point, right, schematic diagram. And this is your what you call when u has been given, when this u has been given, right. So, accordingly you can make it. So, how I have made it from this diagram only, I will not go for left and right, that this portion of course will come to this portion, right, but if from here only we will try to make it, look at that. So, only this u minus here, but we simplify, u plus will be here. How things are? Look, this is delta E actually, this is your delta E. So, that means this is going this way and this delta E is going this way, right. So, if you try to simplify, it will be your what you call, this is your this side will be your this is minus delta F, and this is your what you call it is u, it is minus u, and this is your delta E. So, this is your minus delta E minus u into r will come here, right, yeah, into r will come here, that feedback will go there. Then if you simplify this, then how things are, just have a look. So, this is your minus delta F, and this side is coming r into your delta E minus your, here I am writing this is r, this is delta E minus u, this feedback is coming here, right. So, that means this is your, and minus sign is there. So, it is minus delta F, this with minus delta F, and this is minus r into delta E minus u. Delta this is r into delta E minus u, then you close the bracket. So, output here whatever is coming here it is actually minus delta F minus r into delta E minus your u, right, into your this k upon s is there, right, into k upon s is there, is equal to what, is equal to your this delta E. So, is equal to your delta E, therefore, it is s delta E is equal to your minus k delta F, then multiply this one minus r k delta E plus your, because minus it is plus r k into your u, right. So, this one you bring it to this side. So, s delta E plus r k delta E is equal to r into k into u minus k into delta F. Therefore, you take delta E common. So, it will be your s plus r k delta E is equal to r k into u minus k into delta F. So, divide both sides by r k, right. If you do so, I am making it like this, r k if you divide, it will be 1 plus s upon r k is equal to this, r k will be cancelled. So, r, because this side will be r k plus r k u and minus k upon r k into delta F, that means 1 upon r k is equal to T g, that is the time constant, that here I have missed delta E, right. So, it is 1 plus s T g into your delta E is equal to u minus k will be cancelled, 1 upon r into delta F. That means your delta E and T g is equal to, I have told you, it is governor time constant 1 upon r k, right, and delta E is equal to your u upon 1 plus s T g minus your 1 upon r into your 1 plus s T g delta F, this way. Or the way we have made the block diagram, delta E is equal to, you make u minus delta F upon r into 1 upon 1 plus s T g, right. So, this is your what you call, this is your this thing. So, that means delta is equal to u minus delta F upon r into 1 upon 1 plus s T g. So, that we are making, no, look here the diagram, delta is equal to u, this delta F is coming from somewhere, we will see, u minus delta F upon r into 1 upon 1 plus s T g, it is coming, no, same thing, right. So, from this side we have, because we will this is for the understand purpose, right, and when making the block diagram actually we are going from this right side, we have bring it to left side, and this one we have taken to only this portion, only this portion, this we will see later, right, this part we will see later, right, only this portion. So, thank you very much, we will be back.